Hi, I'm Arvind Bhattacharya. Let me begin with a question. Have you noticed yourself moving your eyes like this when you look out a train window? Your eyes follow a target for a bit and quickly switch to another. From your perspective, it may look like this. The target could be a tree or a car. You follow this for a while and then you quickly switch to another target. Then you maintain your gaze on something else and switch, and so on. What's going on here? Why do we do this? Well, common explanation is that humans are forced to do such movements due to a distinct character of the eye. On the back of our eyes, that is the retina, there's a small region called the fovea. This region has the highest visual acuity, and hence we have to move the eye to expose the fovea to areas of interest. But it turns out eye movements, specifically fixations, are also useful for making sense of the 3D world through a 2D sensor. And this is the key insight here. Fixation also helps in 3D perception, and it is a strong and helpful regularity. Before we continue, we must make the definition of fixation clear. Suppose a camera or an eye is looking at an object. Now suppose it undergoes some translation. In order to center the same object in its visual field, the eye needs to rotate, essentially countering the effect of translation. We call this act gaze fixation, or simply fixation. If we make a robot fixate, we find that it immensely helps in 3D perception. The fixated object could be something it is interested to interact with, such as this red object that needs to be picked up. Now this robot is performing the side-to-side motion to keep itself in continuous motion. In practice, the robot can simply fixate while moving about for other tasks. So, what can a fixating robot do? Well, consider mirrors and reflective surfaces, translucent or see-through objects. These are difficult for depth sensors, and we typically avoid them in robotic vision. But with fixation, these are not a hassle. Like with humans, we don't have trouble around such objects in daily life. We will show that fixation naturally accommodates such situations. Take this situation for example. The robot is tasked to pick up the red object and avoid the see-through object. Here is the robot's perspective. Typical depth cameras will have a hard time here, but fixation allows to simultaneously find the obstacle while estimating distance to the target object. To understand how fixation enables all this, let us first take a look at a simple example. Here are 5 objects, but it is hard to tell their relative depth. However, when a camera starts fixating on the purple diamond, you will immediately see it. All objects behind the fixated object move in the opposite direction of those in the front. This is a simple cue. By observing the direction of visual motion, a robot can perceive the existence of objects in the way. Now, let's see how this works on the robot from earlier. For this, we make use of Optic Flow, whose direction is indicated by colors. So, for example, rightward motion is red, bottom left is green, and so on. When fixating on the red object, all objects in front move in the opposite direction as all objects behind the target object. Or consider this situation with a translucent obstacle. The front lip moves opposite to the background. Similarly, in this situation with a reflective surface, objects in front are clearly separated. This is even true for object reflections that appear to be in front. So, fixation helps to easily and robustly perceive foreground and background objects. But there is more. Fixation also helps in accurate distance estimation to the fixated object. To see this, let us imagine a top-down view of a fixating camera. When a camera translates in a lateral direction, it needs to produce a rotation to counter the shift of an object in the visual field. This rotation is a function of the distance to the object. That is, farther objects produce smaller rotations than nearer objects. In fact, the distance is nothing but the instantaneous ratio of translation to rotation velocities. This is unlike traditional structure from motion, where effects of rotation are usually compensated. We demonstrate that rotation gives valuable information. Importantly, this leads to accurate distance estimation because it results from robot's own movement, that is, proprioception, which is a reliable signal available on most robots. Alright, so far we saw how fixation helps uncover useful information. We can use this information to generate robust robot behaviors. We can make a robot pick up objects without prior knowledge of its size, and on its way, it can avoid complex obstacles while continuously and accurately measuring distances to the target object. In summary, fixation leverages two key irregularities in the geometry of 3D space to robustly determine obstacles and obtain accurate distance estimates. Fixation can be achieved by simply modifying a robot under movement to simply look at the object it may be interested to interact with. We humans also do this without conscious notice. So, with the manipulator robot and an RGB camera, you can add robust 3D capabilities at almost no cost. Obstacle detection can use a basic optic flow algorithm, and distance measurement can use information already available on the robot. So, you can easily integrate fixation into your robotic application. This research was done at the Robotics and Biology Laboratory and Excellence Research Cluster, Science of Intelligence.